Hello, Dr. Horn. This is the Chapter 15 video problem. So for my particular case, I have 0.3067 molar acid with 0.1653 molar base with a pKa of 4.82. We start at 0.0250 liters, and so to find moles, we used the normal molarity equation, and we ended up getting 0.00767 moles after rounding. So at equilibrium, that means that we would have 0.0464 liters. Of course, this is using the same equation. So our Ka, we take our pKa, which is 4.82. We're able to find our Ka from the pKa, which ends up giving us 1.5 times 10 to the negative fifth. We know our equation is going to be that Ha yields the hydronium plus, or the H plus the base. And so we're able to make a nice table. So our first value is 0.3067, other values are nothing. So we're able to form an equation, which we have here. We have x squared over 0.3067. Our x is pretty much negligible since the Ka is so small. And that ends up giving us an answer of x is equal to 2.15 times 10 to the negative third. So if we plug that into the equation, when we plug x into what H plus was, that gives us 2.15 times 10 to the negative third molar. In order to find the pH, we need to take the negative log of whatever that was, which ends up giving us the pH of 2.67. So the volume at equilibrium we know is 0.0467, but we want to know what the pH would be at 1/3 of that. So our new volume would be 0.0155 liters of what base is added. And we know that the total volume after that is going to change it to 0.0405 liters. That's summing the initial volume plus the added base volume. So now we need to figure out the moles of the base. So if we have 0.0155 liters, what we did, what we calculated for the 1/3 of the equilibrium amount, you multiply that to the molarity, and that gives us 0.00256 moles. And we're able to solve for the information that we need to put into the Hasselbalch equation. So the difference of the moles gives us 0.00511. And our we're able to take the molarity of both the base and the acid. So we have 0.00511 over 0.0405. And also the acid, which ends up, or the base, I'm sorry, that was flipped. And our base would have a 0.063 molar, and our acid 0.126. And we plug that into the equation, and ends up giving us a pH of 4.52. We move on to step C, and we want to know what the pH and volume is at 2/3 of equilibrium. And so we solve for the liters, which ends up giving us 0.0309. We want to find moles, and so we use the same equation to give us 0.00511 moles. Our total volume now is 0.0559 liters. We need that to calculate the molarity. Our difference of moles is going to be 0.00256 moles. So our molarity of B, once we find our difference of moles, our base is going to be 0.00511 divided by 0.0559, which ends up giving us 0.0914. And we do the same thing to the acids, which gives us 0.0458. We plug that information into the Hasselbalch equation, and we get a pH of 5.12. For D, we need to know the 99 out of 100 of our equilibrium and our pH. So we do the same thing we've done before, and we get 0.0459 liters. Our total volume now is 0.0709 liters. So our base ends up being, we take the molarity times what we calculated for here, and that gives us our new molarity 0.00759, and the difference of moles gives us 0.00008, which is 8 times 10 to the negative fifth. We plug that into the equation and we get a pH of 6.8. So we are gradually getting nearer to 7. So now we're at equilibrium. Okay, we know that our equilibrium of liters is going to be 0.0464, and we know that they both need to have 0.00767 moles to be at equilibrium. So our total volume at this stage, we're going to take our initial volume plus our volume of base at equilibrium, which is 0.0714 liters. Okay, we plug all of that into the molarity equation. We end up getting 0.107 molar of base. And now that we're at equilibrium, we're able to find what our Kb would be. So we have our water constant equation, and we're able to solve for Kb, and now we're able to make a new ice table. This is our new equation, and we know our molarity is 0.107 for the base. And so once we plug all of this information into, once we make the equation, the quadratic, we end up getting an x of 8.45 times 10 to the negative sixth. And once we solve for the negative log of that base, we get 5.07. We need to take 14 minus that of that pOH, which ends up giving us is 8.9. That's our new pH. So now we're past equilibrium. We have a 101 over 100. That's the amount of liters that we want. We have 0.0469. That's our new volume. We need to solve for our moles, 8.0 times 10 to the negative fifth. Our difference of, or our new total volume is 0.0719. And now we know what our difference of moles is, which is 8.0 times 10 to the negative fifth. We need to find the new molarity, and which ends up giving us 1.11 times 10 to the negative third. We put that into an equation that says pOH is equal to negative log of whatever this is, or the OH, the base. And that gives us pOH of 2.95. And now we need to find out what the pH is by finding the difference from 14, which gives us 11.05 for the pH. For G, it is very similar what we're doing, taking 4/3 of whatever the liters, the volume was, equilibrium, which is 0.0619 liters. Find the difference of moles. This is our new quantity of moles. We have our difference of moles here, which is 0.00259 moles. We take whatever that amount of moles was divided by the total volume, which ends up giving us was 0.029 molar base. And so we are able to plug it into the same equation that we did before. The pOH is equal to negative log of the base, and that gives us 1.538. So 14 minus that gives us 12.46. Now we have 5/3 of that volume and the pH. So we need to take our volume at equilibrium, solve for the 5/3 of that, which is 0.0773 liters. Our total volume after that is going to be result in 0.1023 liters. We need our new amount of moles by using the molarity equation, which gives us 0.0128. We're able to find the difference of moles, which is 0.0128 moles minus our 0.0767 moles, whatever we had at equilibrium, and that results in 0.00513 moles. We're able to find our new molarity with our total volume, which gives us 0.0518 molar. And with that, we're able to find our new pOH. We plug that into the equation, which gives us a pOH of 1.29. We're able to subtract that from 14, which gives us 12.71 as our last pH in this problem. Thank you.